Today we are starting with one topic of paper 2, that is complex numbers. What are complex numbers? Now basically this is something new. We have discussed prime numbers, even numbers, odd numbers, and rational numbers, irrational numbers, real numbers, but complex numbers is very new. Now if I am forming an equation for, let's say, ax square plus b equal to 0. So this is ax square equal to minus b. And here you are taking x square is equal to minus b upon a. So when you are taking the square root, this minus remains. Let's take an example. X square plus 1 is equal to 0. So x square is equal to, when this comes here, the sign changes and this is your minus 1. So x square is equal to minus 1, and after that you would see when you are taking square roots, what happens? X is equal to plus or minus, but this minus 1 goes inside the square root. Now this is something which was not defined at all. Not at all. So when I am writing a linear equation for ax square plus b equal to 0, and I have formed a real root, that is for minus b upon a, what happens? The solution I derived for x was plus or minus again root of minus b upon a. Now when I am taking this example, this is something which I have not defined, neither described, neither I have studied till now. So this concept was derived as imaginary concept, an imaginary part of a number which I am learning. This imaginary part was basically the square root of x, which is square root of minus 1, which is new, completely new. So this root of minus 1 was imaginary, which was defined by our great mathematicians, and here I would say 1 into minus 1, that is 1i. So this I is equal to root of minus 1. So I denotes what? I denotes your imaginary part again, starting with I, as I said, I denotes with imaginary part, and this imaginary part was I representing root of minus 1. So I square was equal to I into I, which is root of minus 1 into root of minus 1, that is minus 1. This root goes away. I cube was defined as I square into I. So basically I am finding the values. Minus 1 into minus 1, root of minus 1. Now this, when you write, it's of no use. So we will keep this as I, minus 1 minus I raised to 4 is I raised to 4 the whole square I square into I square. So that is minus 1 square, that is positive 1. I raised to 5 is I raised to 4 into I, that is 1 into minus 1 into I, that is I. I raised to 6 is I raised to 4 into I square. So here we are adding basically multiplication, law of indices. Here you will write as let's say 1 into minus 1, that is minus 1. So any multiple of 4 for I, your answer will be positive 1. So let's say I raised to 32, you will write I raised to 4 raised to 7, so positive 1 raised to n. Any power for a positive number will always be positive. I say I raised to 34, here you will split as I raised to 32 into I square. You have the value we find right now, that is minus 1. So this is little bit concepts for I and how we will get the values. So in future when we will solve the sums, that time this will help us out. Now again starting with I, so it denotes imaginary part of a number, and when this part is combined, the imaginary part is combined with real plus imaginary, what happens? A new number, a new type of number was derived, that is your complex numbers, which is represented as Z. So as I said, real part, where I am writing the denotation by RE, and here I am writing IM. So Z was real part of imaginary number plus imaginary part of real number. So it was derived in the form of A plus BI, where this is your real part and this is your imaginary part. Again, so written as A plus BI. So Z is equal to A plus BI is in the form. So there are certain combinations when I say A is my real part and B is my imaginary part. So example, 3 plus 12, A is 3, B is 2. One more example, 9 minus 7, here again A is 9 and B is minus 7. Now this you will split in the original form, that is A plus BI. Again third one, one more example, 5 plus let's say 9i or root of 9i. Here when you write this, there is a difference I want to show you. 4 plus root of, let's say I am writing minus 9. Here when I write this, A is 5 and B is your root 9, but here I have to derive the A and B part, that is the real and imaginary part. Here I am writing this as 9 into minus 1. So that is root of 9 into root of minus 1. Let's split up. So this is 5 plus 3i. This is how you will derive it, and hence A is your 5 and B is your 3. Okay. Further, one more example, root minus 17. You will split as 17 into minus 1, that is root 17i. So B is 7, root 17, and here you will see the real part is not given, that is 0. So here we are discussing the properties first property or certain combination, I would say. So when real part is given, only it is completely, or I would say purely real, right? So when I would say real part is given only, so let's say only 5 is given, so it is purely real, right? And when imaginary part is given, so your real part is given and your imaginary is not given, so imaginary is 0. Your imaginary is given, so real will be 0 and imaginary will be some value, any value. Okay, such type are purely imaginary. There are certain combinations, as I said, of real part plus imaginary part. So when I'm combining both, you get a complex number, which we discussed in the early examples. After that, I'm denoting this as z plus abi, and here I'm writing bar z is equal to a minus bi. Now what is this bar z? It is the conjugate of complex numbers. So bar z will be conjugate. How will I define conjugate? The sign is interchange for imaginary part of a complex number. As in, if I am writing z is equal to a plus bi, which I have shown you, I have written bar z as a minus bi. What I did, I just changed the sign of the imaginary part. We discussed what is real part, we discussed what is imaginary part, we did certain examples, we found a and b. Here we have a plus bi and a minus bi. So what I did, I interchanged the sign of the imaginary part of a number. So if z is a minus bi, then bar z is a plus bi. As simple as that. So let's take an again example. 5 plus 3i is my z. So bar z will be 5 minus 3i. Simple. If I will say 9 minus 7i, I would say here as 9 plus 7i. Z bar z. And here, if I am taking only, let's say, real part as in your imaginary is 0 and only 7 is given. So 0i plus 7 you would say, or 7 plus 0i. You are writing this as 7 minus 0i, that is 7. So here it doesn't make a difference. But if I say 5i, here I will write in the form of 0 plus 5i. This is my real part. This is your imaginary part. Let's say this is b. So z is 0 plus 5i. So bar z is 0 minus 5i. equality of complex numbers. A plus bi is equal to c plus di, then real part A and C is same, imaginary part bi is equal to di, therefore b is equal to b. So your real part is together and your imaginary part is together, then the values will be same. Now properties. For complex numbers. There are 4 sections here. I would say addition, when I am adding, when I am subtracting, when I am dividing, and when I am multiplying. If I am adding two equations, let's say z1 is a1 plus b1i and z2 is a2 plus b2i, and when I am adding both of them, I'll write as z1 plus z2 is a1 plus b1i plus a2 plus b2i. Hence here I would say a1 and a2 real part together, b1i plus b2i imaginary part together. So example, 5 plus 7i is z1 z, and z1 let's say 9 minus 7i. So if we are adding both of them, what will happen? We are taking real part together. This is your a, 7i minus 7i. This is your b, what would happen here? 14 plus 0i. So the answer is 14. It is purely real. This was just an example. One more example we would take. Minus 2 plus 5i plus 5 minus 9i. So, real part together, and imaginary part together. Three plus minus 4i. So your a is 3 and b minus 4. Okay. After that, if I am taking three values z1, z2, z3 or three type of complex numbers, first one I would say z1 plus z2 is equal to z2 plus z1. Second, z1 plus z2 plus z3 is equal to z1 plus z2 plus z3. And third, if I am adding z1 plus 0 or 0 plus z1, the answer will remain the same. Again we did conjugates, we discussed little bit of it. So when I am combining a complex number and its conjugate, what happens? 2 times of real number, your answer arises, right? So for this I am giving you an example. 2 plus 3i, usko you are adding with 2 minus 3i with its conjugate. Let's say z1 is 2 plus 3i. Your bar z, or that is your conjugate, will be 2 minus 3i. What happens? 2 plus 2, I am taking real part together, imaginary part together. We We solved such kind of example earlier. It is purely real. But it was 2 times your real number. Real number is A. This is how we got the answer. 4 we got, but it was 2 times the real number which you are defining in your equation. After that, subtraction properties. Subtraction, we are again taking 2 type of questions here. Let's say Z1 is A plus BI, Z2 is A2 plus B2I, and Z3 is A3 plus B3I. So Z1 minus Z2 is A1 plus B1I minus A2 plus B2I. Here, real part together, imaginary part together, whatever is your answer. But you will split first both of them and then you are writing your answer. Example. Four plus I minus 2 minus 3I, that is 4 minus 2 plus I, यहाँ पे sign will change, minus minus will become plus. So 2 plus 4I, that is A, and your B is 4, real part and imaginary part. Clear till here. After that we are moving with the properties for your multiplication. What will happen? Let's say I am defining Z1 and Z2, and Z1 is your A1 plus B1I, A2 plus B2I, when I am taking the product, A1 plus B1I, A2 plus B2I. Let's open the bracket. Here I square is equal to minus 1, we discussed. So this plus will change to minus B1, B2. We will take an example to follow it much simpler. Okay. So let's say Z1 is your 5 plus 3I and Z2 is 7 minus 9I. You are multiplying both of them. 5 plus 3I, 7 minus 9I, 7 5s are 35, minus 45I, plus 21I, plus minus minus 27I square. Here you will see 35 I am writing as it is, minus 45 plus 21I. What happens? The answer comes to minus 24I. यहाँ पे minus minus becomes plus because I square is equal to minus 1. So minus minus plus 35 plus 27 will give you 62 minus 24i. This is how we will find the product for respected function. Starting with algebra of complex numbers. First one is addition of complex numbers. So here z1 is equal to a plus b1i, z2 is equal to a plus bi2, let's say, or b2i, let's say. Then z1 plus z2 is a plus b1i, this is 1, this is 2, plus a2 plus b2i, that is, so a1 plus a2 plus b1i plus b2i. So real part is together, imaginary part is together. Let's take an example. Minus 2 plus 5i plus 3 minus 7i. Then here your answer will be minus 2 plus 3 plus 5i minus 7i. So 1 plus minus 2i, that is 1 minus 2i. So here this is your real part. 1 minus 2i, here 1 is your real part and minus 2 is your imaginary part. That is a plus minus bi. So here 1 plus minus 2i. This is the form of complex numbers. After that, certain properties. Z1, Z2, Z3 all are in the form of complex numbers. First I would say Z1 plus Z2 is equal to Z2 plus Z1. Second, Z1 plus Z2 plus Z3, Z1 plus Z2 plus Z3, Z1 plus 0 is equal to 0 plus Z1 is equal to Z1, Z1 plus negative of Z1 is 2 times of real of Z1, and fifth, Z1 minus negative of Z1 is 2 times of imaginary of Z1. These are certain properties of addition. Now let's start with subtraction of complex numbers. Z1 is equal to a plus b1i, Z2 is equal to a2 plus b2i, Z3 is equal to, let's say, a3 plus b3i. So basic subtraction, let's say Z1 minus Z2, so it will be a1 plus b1i minus a2 plus b2i, a1 plus b1i minus a2 minus b2i. So a1 minus a2, this is again your real part, plus b1i minus b2i. This is your imaginary part. So again an example, 4 plus I minus 2 minus 3i. So here 4 minus 2 plus 1 plus 3i. This is your real part again. You are taking real together, imaginary together. So 2 plus 2i. Next is your multiplication. Complex numbers. If I say Z1 and Z2, and let's say Z1 is defined as A1 plus B1i as the earlier example, and this is A2 plus B2i, you will solve it as A1 plus B1i into A2 plus B2i. That is A1 A2 plus A1 B2i plus A2 B1i plus B1 B2i square. Now, before we start with the multiplication and finding answers, let's revise. We have I is equal to root of minus 1. Hence, I square will be written as I into I, that is root of minus 1 into root of minus 1, that is minus 1. Only your square root will go away. I3 is I square into I. So minus 1 into I is minus I. I raised to 4 is I square into I square. That is I raised to minus 1 into minus 1, that is positive 1. So any power multiple of I of 4, that is I raised to 4 raised to 2, or let's say I raised to 4 raised to 3. So this is I raised to 8, I raised to 12. Your answer will always be positive plus 1. But if it's square, let's say I raised to 5 raised to 10, you can write as I raised to 8 into I raised to 2. You know your answer is always positive 1. I square is minus 1, and here you get minus 1. Again an example, I raised to 31, let's say. So this is I raised to 4 raised to 7 into I raised to 3. There is I raised to 28 into I raised to 3. Again, this is multiple of 4. So here you will get 1 into minus I, that is minus I. That way you will solve. Again, you should know A plus BI, if I am writing, A is the real part, B is the imaginary part. So for 3 plus 2i, A is 3 and B is 2. Let's say it is 5 minus root 7i. A is 5, B is root minus 7. Let's say plus 2i. So A is 0, B is 2. Let's say I'm writing 5. So A is 5, B is 0. let's say 4 minus 7. So this is 4 plus minus 7. If I am writing in the form of A plus BI, then A is 4 and B is minus 7. So when you are writing the product, as in the multiplication of your complex numbers, you got your answer as A1 A2 plus A1 B2I plus A2 B1I plus B1 B2I square. So here the sign will change. Minus B1 B2. Then certain again properties we will discuss. Z1 into Z2 is equal to Z2 into Z1. Z1 into Z2 when multiplied with Z3, it is Z1 at one side, Z2 into Z3. Z1 into 1 is equal to 1 into Z1 is equal to Z1. Z1 when negative multiplied with complex number, it is again purely real, whereas if I am taking the conjugate, so this negative I am repeating again and again. So this negative is nothing but, let's say if Z1 is A plus BI, then Z1 bar is the conjugate which I am repeating, that is the negative part. So basically it is the conjugate which we are discussing again and again. So Z1 into bar Z1 will always be your A square plus B square. Okay. Now so Z you all are representing as the complex number, and the negative part, as I am saying, this is your bar Z, is the conjugate of respected complex number. Let's take an example. Let's say 3 plus 2i and 3 minus 2i. If this is Z and this is your bar Z, that is negative, what will happen? You'll open your brackets, how you were opening in your lower standards. 9 minus 6i plus 6i, and here we are writing minus 4i square. That is basically A plus BI, A minus BI. Now earlier what we did is A square minus B square. That was the formula when I write A plus B, A minus B. But here, since I square, the value is minus 1, this becomes plus, and hence also in your earlier we will write plus. So there a little difference arises. So 9 minus of minus 4 will give you 13, which is your A real part. Now multiplication, certain properties are there for this, for Z1, Z2 and Z3. If I am taking Z1, Z2 into Z3, this is equivalent to Z1, Z2, Z3. Z1 into Z2 is equal to Z2 into Z1. Z1 into 1 is equal to 1 into Z1, that is equal to Z1. And if you are taking the conjugate, then your answer will be purely real. Okay, so let's take an example for this. It will be in the form of a square plus b square, but no part of imaginary will exist. No part of imaginary will exist means no I in your answer. So Z is 5 plus 7I. Z1 bar or bar Z1, the conjugate of this part is 5 minus 7I. Here, so 25 minus 35I plus 35I minus 49I square. So 25, this just gets cancelled, minus 49I square. I square is minus 1. So 25 minus of minus 49, that is your 73 is your answer. So what happened? You are taking a square plus b square. Here you saw a was 5 and b was 7. Now when I am taking square, whether it is b is minus 7 or plus 7, your answer for square will remain positive. So here it doesn't make a difference. Next we are starting with division. Z1 is A1 plus B1I. Z2 is A2 plus B2I. When I am dividing Z1 upon Z2, that is A1 plus B1I upon A2 plus B2I, you are taking the conjugate of the denominator, you are multiplying and dividing with the conjugate, and then I am opening the brackets. So A1 A2 minus A1 B2I plus A2 B1I minus B1 B2I square upon, this is in the form of A plus B, A minus B, that is A square minus B square, right? So A1 A2 minus A1 B2I plus A2 B1I. Here I square is minus 1, so their sign changes, upon A square, sign will change, I square is minus 1, minus minus plus. So this is the basic division property. So whenever division or your question says you have to solve the following, or you have to get the real part and the imaginary part for the question, and when division is given something upon something, you will take the conjugate of the denominator, that is opposite sign of the function of your complex numbers of denominator, that will be multiplied and divided, and you will proceed with the question. So now let's start with little bit of question sections. First we are discussing conjugates. conjugate of, let's say, 5 plus 6i. It is 5 minus 6i. Second, let's say minus of root of minus 5. Here you would see minus is given. When I say the real part and imaginary part, what happens? Your real part is 0, it's not given. So this is basically in the form of minus 5 into minus 1, that is 0, minus root 5i. Now when I have to take the conjugates, I would define this as 0 plus root of 5i, that is your root 5i. So this was a little bit different. One more, let's say 5i. This will be a 0 minus 5i, that is minus 5i. As simple as that. Now, this is how much we have done. Alright. Conjugates we did till now. We defined the properties, the algebra of complex numbers, that is addition, subtraction, division, multiplication. We distributed the real part and the imaginary part. Proceeding with that part, we come with two new concepts, that is modulus and amplitude. Now, for modulus, you have to put this z in modulus. What was modulus? Any number, it changes positive. You are taking a square plus b square of that particular function, and amplitude, that is z, is defined as tan inverse of b upon a. These two things you need to remember. Example, let's say I am taking 7 minus 5i. Modulus of z would be a square plus b square. Here in this, a is equal to 7 and b is equal to minus 5, because this is in the form of a plus bi, and you are splitting this as 7 plus minus 5i. So 7 the whole square plus 5 the whole square, that is 49, plus 25, that is root of 73. And when I have to find the amplitude of it, I would say tan inverse of b upon a, that is tan inverse of minus 5 upon 7. Right. So, as simple as that. You will keep it as it is. One more example we are taking. Let's say we would take root 3 plus root 2i. So, again, modulus a square plus b square, that is a is root 3 here, b is root 2. You take root 3 the whole square plus root 2 the whole square, that is 3 plus 2 is equal to root of 5. And here tan inverse of b upon a, that is root 2 upon root 3, tan inverse of b upon a, that is tan inverse of root 2 upon root 3. So tan inverse of root 2 upon 3. That is the direct form for writing this amplitude. Alright. Now, we are taking, let's say, example let's take root 3 minus I. Here, what is your A? Root 3. Your B is minus 1. So, modulus z is equal to a square plus b square. Next, you are putting the values for it. So root 3 the whole square plus minus 1 the whole square, that is 3 plus 1 is root of 4, that is equal to 2. Now since it is modulus, negative option doesn't arise here. Completely it will be positive. You are finding the amplitude of z, that is tan inverse of b upon a, that is root 3 your, let's continue on the next page. So tan inverse of minus 1 upon root 3, this value is minus of 10 pi by 6. Pi by 6 is nothing but your tan 30. So tan inverse of tan 30. Okay, after that tan inverse of tan 360 minus will give me minus tan 30. So you have to remember your trigonometric functions which you have done. 2 pi minus theta is equal to minus 2 tan theta, where you have to get this negative, and in tan it is possible for 2 pi minus theta. Okay, so 360 minus here you have done. After that, what is the answer for it? Tan inverse of, you are taking LCM and everything, so you are getting 10 of 11 pi by 6. One more trigonometric functions we have done. Tan inverse of tan theta is theta, so here your answer is 11 pi by 6. One more example for this tan type of data, so that we are much clearer for it. We have z is equal to minus 3, 1 minus I, that is minus 3 minus 3i. So here your a is minus 3 and b is also minus 3. Why? Because you are writing this in the form of minus 3 plus minus 3i in the form of a plus bi. So your values are clearly indicated. You can write that step. But when it goes in modulus, we are writing it square. So minus 3 the whole square plus minus 3 the whole square. Root 18, that is nothing but 9 into 2, that is 3 root 2, that is your modulus. For amplitude, tan inverse of b upon a, both were root minus 3 and root minus 3. This minus minus goes away. So tan inverse of 1. Here tan inverse of minus tan theta, tan inverse of minus tan 45. So tan inverse of tan 180 minus theta, that is tan inverse of 10 pi minus pi by 4. Taking LCM, tan inverse of tan 3 pi by 4. Again, tan inverse of tan theta is theta, that is 3 pi by 4. That is your amplitude for this question. Now express following in the form of a plus bi, where a and b belongs to real numbers. Example, 1 plus 3i, 1 minus 3i. You will open the bracket, 1 minus 3i plus 3i minus 3 3s are 9, I square, but I square is minus 1. So 1 minus 3i plus 3i minus 9i square. I square was minus 1. So 1 minus minus 9, that is 1 plus 9 is equal to 10. I 4 plus 3i upon 1 minus I. First you will open the bracket, 4i plus 3i square upon 1 minus I. I square is equal to minus 1. The values was discussed. Upon 1 minus I. So you have the product in the form of 3 plus 4i upon 1 minus I. Whenever in division, in the form of division, we have to take the conjugate of denominator. So 3 plus 3i plus 4i plus 4i square upon 1 square minus I square. So that is 3 plus 7i plus minus minus I square is minus 1. So you will write minus 4 upon 1 minus, again I square is minus 1. So here you are getting minus 1 plus 7i upon 2. Now I have to write the real part and the imaginary part in the form of a plus bi. We will split the function as minus 1 upon 2 plus 7i upon 2. Here you get your a, here you get your b, bi. So here you get b as 7 upon 2. One more example, 4i raised to 8 minus 3i raised to 9 plus 3 upon 3i raised to 11 minus 4i raised to 10 minus 2. First of all, we have to find the values for I raised to 8, that is I raised to 4 square. Any multiple of 4, your answer will be positive 1. I raised to 9 is I raised to 8 into I, that is 1 into I is I. I raised to 11 is I raised to 8 into I raised to 3, that is positive 1 into minus I is equal to minus I. I raised to 10 is I square raised to 5. I square is minus 1 raised to 5. Negative number raised to any power of odd number, your answer will remain negative as it is. Now, substituting the values, we get 4 into 1 minus 3 into I plus 3 upon 3i raised to 11, that is 3 into minus I, minus 4 into minus 1 minus 2. So 4 minus 3i plus 3 upon minus 3i plus 4 minus 2. 7 minus 3i upon 2 minus 3i. Whenever in the form of division, you will take the conjugate of the denominator and multiply and divide with it. So 7 minus 3i, 2 minus 3i into 2 plus 3i upon 2 plus 3i. Opening the brackets, 14 plus 21i minus 6i minus 9i square upon 4 minus 9i square. I have opened the bracket, a minus b, a plus b. So 14 plus 15i minus minus plus, because I square is minus 1, minus minus plus upon 4 minus I square is minus 1 again. Here you get 23 plus 15i upon 13. Splitting both of them to get the real part and the imaginary part, you will get in the form of a plus b. So a is 23 upon 3 and b is 15 upon 30, to get in the form of a plus bi. Expressing in form of a plus bi for the following. Example, 3 plus 2i upon 2 minus 5i plus 3 minus 2i upon 2 plus 5i. Here, we need to first solve the equation. That is 3 plus 2i then 2 plus 5i plus 2 minus 5i into 3 minus 2i upon 2 minus 5i, 2 plus 5i. Open the brackets. 6 plus 15i plus 4i plus 10i squared plus 6 minus 4i minus 15i plus 10i squared upon, this is a minus b, a plus b the whole square, that is a square minus b square. Solving the equation, 6 plus 6 is 12 plus 15i minus 15i gets cancelled, 4i minus 4i gets cancelled. Here you get 20i square upon 4 minus 25i square. 12 plus 20 into I square is equal to minus 1. Again, 4 minus 25 into I square is equal to minus 1. That is minus 8 upon 29. Here you get only the real part. So your imaginary part is purely real. Imaginary part is 0. Hence, in form of a plus bi, we get minus 8 upon 29 plus 0 into I. So this is your a and b is equal to 0. Next, 2 plus root of minus 3 upon 4 plus root of minus 3. We have to write in the form of a plus b. So here you will multiply with the conjugate of the denominator. First of all. After that, let's split this. So 2 plus 3 into minus 1 upon 4 plus 3 into minus 1 into 4 minus 3 into minus 1 upon 4 minus 3 into minus 1. Next, we have already studied I is equal to root of minus 1. So here I am splitting both of them. we know that I is equal to root of minus 1. So 2 root 3I upon 4 plus root 3I into 4 minus root 3I upon 4 minus root 3I. Now opening the brackets, here you get 8 minus 2 root 3I plus 4 root 3I minus 3I square upon a plus b, a minus b, 16 minus 3I square, that is 8 minus 2 plus 4 is plus 2 root 3I minus 3I square upon 16 minus 3I square. So 8 plus 2 root 3I minus 3 minus 1 upon 16 minus 3 into minus 1, that is 11 plus 2 root 3I upon 19. When you split the numerator and the denominator, you get 11 upon 19 plus 2 root 3 upon 99. So a is 11 upon 19 and b is equal to 2 root 3 upon 19. So this is basically you are splitting to get your a and b. Next one, when we proceed, we get provings here. Question similar to proving. Prove that. Let's see. X plus I by the whole cube, y plus bi, show that y upon x plus b upon y is equal to 4x square minus y square. Again here, starting with what is given, starting with the left hand side, I would say x plus yi the whole cube, that is equal to a plus b the whole cube. So here you get x cube plus 3x square yi plus 3xy square I square plus y cube I cube. When you illustrate, 3x square by I plus 3xy square, I square is minus 1, y cube into I cube is minus I. We have discussed the values. So, x cube plus 3x square y minus 3xy square minus I by cube. Here we have been given this is equal to this. We have to prove that. Now here, if this is the given condition, I would equate x plus 3x square y minus 3xy square minus y cube I is equal to y plus vi. We will split the real part together and the imaginary part together. So 3x x cube minus 3xy square plus 3x square y minus y cube I common is equal to y plus b. So splitting both the equations and taking real part together and imaginary part together. Here you get y is equal to x cube minus 3xy square. On the other side, 3x square y minus y cube I is equal to vi. I gets cancelled. Here you get x is common, so x square minus 3y square, and your x comes in the denominator. You get x square minus 3xy square. Again here v upon y is common, so 3x square minus y square is equal to 3. This y comes here, you get x square minus y square. In proof that you have been said y upon x plus v upon y. So adding equation 1 and equation 2, depending on what you need to prove. You get x square minus 3y square plus 3x square minus y square. So 4x square minus 4y square, that is 4 common. That is how you proved for your y upon x plus v upon y. Find the value of here. We will take an example. Let's say x cube minus x square plus x plus 46 if x is equal to plus 3i. So this is basically a 3 to 4 mark question. If this is given, it's a 3 mark question. When x is equal to something where you have to conjugate with, you have to rationalize basically your numerator and denominator with the conjugate of the denominator. That time it will be a 4 mark question, otherwise it is 3 mark question. So 3 to 4 mark question. But your steps will remain the same. First step would be starting with x. Here you need to take this 2 here. So x minus 2 is equal to 3i square. So basically I am taking the terms together and imaginary part at the other side. Taking squares on both the sides. What you get is x minus 2 the whole square is equal to 3i the whole square. A minus b the whole square, that is x square minus 2ab. A square minus 2ab plus b square, that is plus 4. And here you get 9i square. So x square minus 4x plus 4. I square is minus 1. And when this minus 9 comes here, it becomes plus. So what you get is x square minus 4x plus 4 equal to 0. After this, at a school level we have studied what is called as synthetic division. Here you will apply that synthetic division and get the answer. You will divide your this equation with this equation. Now this will be your divisor and this would be your dividend. Right? So x square minus 4x plus 30 divided by x cube minus x square plus x minus 46. Here x square into what will give you x cube? So that is your x, and which will be multiplied with every element. So x square into x is x cube. By default this is your minus. Minus 4x into x is again minus 4x square plus 13x minus plus minus, this gets cancelled, minus minus plus minus. So here you get 3x square minus 12x minus 46 plus 46. After that, x square into what will give you 3x square. Now you have to see this. So here you will multiply with 3 definitely. But which 3? Plus 3. Already a minus is there. Minus 12x plus 39. This will get cancelled, this will get cancelled. What remains in your denominator is 7. Again in your lower standards we have done dividend is equal to divisor into quotient plus remainder. But your already divisor is given as x square minus 4x plus 30 into x plus 3. And your remainder is 7. But this equation is equal to 0 from 1. So 0 into x plus 3 plus 7, that is plus 7. This is one type of examples for your value of x. One more example. Let's say, x cubed plus x square minus x plus 22 if x is equal to 5 upon 1 minus 2y. How will you proceed? As I said here, we will take first x. Here we will take the conjugates of the denominator. You will multiply and divide with it. Next step would be a minus b, a plus b is a square minus b square. So that is 5 plus 10i upon 1 minus 4i square. That is 5 plus 10i upon 1 minus 4 into minus 1. That is 5 upon 10i. That is how you got your answer for the. Here you can take 5 common. So this gets cancelled. X is equal to 1 plus 2y. You will get this one here. X minus 1 is equal to 2y. Taking squares on both sides, you get x minus 1 the whole square, 2y the whole square. So the answer is x square minus 2x. Right? Plus 1 equal to 4i square. X square minus 2x plus 1 equal to 4 into minus 1. So x square minus 2x plus 1 minus 4 equal to 0. The answer you get is x square minus 2x minus 3 equal to 0. You will divide with this part. Now when this minus comes here, it becomes plus. So we will divide now. What you get is, again same thing, x square into what will give you x cube. So you will get x cube minus 2x square plus 5x. So minus, this gets cancelled, minus plus minus, here you get 3x square minus 6x plus 22. Again you will multiply with 3, so 3x square minus 6x plus 15. What remains is your 7, because this gets cancelled, which is plus, this is minus. Again dividend is equal to divisor into quotient plus remainder. So x square minus 2x plus 5 into x plus 3 plus 7. So 0 into x plus 3 plus 7 over 7. Now the next part is getting the values, the part. So you just have to get the values. Let's say I93, how will you get? So that is I raised to 4 into 23 into I. That is I raised to 92 into I. No, I raised to 4 we have discussed is equal to 1. So the answer is I, but positive I. Again, let's say I raised to 8. I raised to 4 into 2, so that is 1 raised. Again answer the remaining one. I raised to 35. I raised to, let's say, 32 into I cube, you can say. So 1 into I cube is minus I. So simplify it as much as you can and get the answer. Evaluate. Root of minus 16 plus 3 root minus 25 plus root of minus 36 minus root of 625. How will we solve this? Again, this will split to 16 into minus 1, 25 into minus 1 plus 36 into minus 1 minus 625 into minus. What you get is root 16 is 4i, so minus 1i. Root of minus 1 is I plus 3 into 5i root 25 plus 6i minus 25i. When we solve this, you get 4i plus 6i minus 25i, which is nothing but 0. So that is evaluation. Now let's discuss some of the theorems. Theorem. So here, first one is n belongs to set, that is set of all integers. Then cos theta plus I sin theta raised to n is equal to cosine theta plus I sin theta. Next, if n belongs to Q, that is all rational numbers, then what you get is cos theta plus I sin theta raised to n is equal to cosine theta plus I sin n theta. Cos theta plus I sin theta raised to minus n is equal to cosine theta minus I sin n theta. Next, cos theta minus I sin theta raised to positive n. Here you get cosine theta minus I sin n theta. Again, 1 upon, if everything goes in denominator, raised to 1, let's say, this is cos theta minus I sin theta. And if we say cos theta minus I sin theta raised to minus n, then your sign will change. Your sign will change. Next are the properties. Next part is the square root. Let's say x plus yi is equal to root of a plus bi. This is how we will solve. Find the square root of complex numbers. So first of all, you have to compare with a plus bi, square root of a plus bi. To remove this square root, you are taking squares on both sides. What you get is x plus yi the whole square is equal to a plus bi. Here you get x square plus 2xy plus y square I square is equal to a plus bi. Here x square plus 2xy I square is equal to minus 1. This is the real part and this is your imaginary part. So taking real part together and imaginary part together, what you get is x square minus y square is equal to a, and at the other side you are adding 2xyi is equal to bi. What you get is x square minus y square is equal to a, and here your I gets cancelled. You get this as b. So this is how you will define for square root of. Next is the properties of conjugates, which we have discussed little bit. conjugate of z will be similar. Okay, z plus z is 2 times of real z. Z minus z is equal to 2I, that is imaginary times 2 times of imaginary number. When both are equal, it will be purely real. And if when I'm adding both, it is purely imaginary. Purely imaginary. When I'm multiplying, it will be real square plus imaginary square. When I'm adding the conjugate, I can split those two. I can multiply both of them. Right. These are certain properties of conjugates. Now discussing the properties of the modulus. Properties of the modulus. Okay. Let's discuss the properties. Modulus is equal to 0. Then real part of imaginary is equal to imaginary part of z is equal to 0. Here z is equal to minus of z. Modulus of z is equal to modulus of negative z. Z into z1 is equal to z square. Next, minus modulus. Your real will be greater than this and less than modulus. So real will be greater than negative of modulus and less than positive of modulus. And similarly, for we can define the function for imaginary. Z into Z, that is conjugate of Z, will give you modulus square. Z1 into Z2 is equal to Z1, Z2. These are certain properties that we say. Z1 plus Z square will give you, Z2 square will give you Z1 the whole square plus 2Z1 Z2 plus Z2 the whole square. So when I am multiplying this will be purely again real. When you are subtracting and the squares are taken, that time again Z1 the whole square minus 2 times of Z1 Z2. So again here you get real, right? Plus Z2 the whole square. Next, Argand's diagram. Here, when we have 2 points, that is x and y. X represents the real part and z represents the imaginary part of the number. So, any function, as I said, if I am denoting first one on x-axis and second one on y-axis, this will be real and this will be imaginary. So, it will be in the form of x plus y. So, your x is representing the real part and the y is representing the imaginary part. After that, we will discuss certain functions. Let's say here, if they are purely positive, it will be in the first quadrant. So your function will rise on the real list. If one is negative and other one is positive, it will be in the second quadrant. So your function will as scenario because this is positive, negative, positive, negative. If your function is minus a minus b, it is purely in the third quadrant. Scenario. Okay. And the next one, that is the last one, a minus b, it will be purely in the fourth quadrant. So somewhere here. Argument for z minus tan inverse of a upon, that is what we discussed. Polar form. Your function is z is equal to r cos theta plus I sin theta. So have you got this? Your cos theta is equal to a upon r and the sin theta is equal to b upon r. So this is cos theta, that is a, and sin theta into r equal to b. R will take common and this function comes. That is polar form. After that, let's say if p is purely a comma b, your a is greater than 0, b is equal to 0, your z will be equal to 3 and z will be 0. First function. Second, if p is a comma b and lies on negative direction of x-axis, so a is less than 0, b is equal to 0, and z is equal to minus 2, and is equal to 5. Okay. After that, if p is a comma b and it lies on the positive direction of our axis, what you get is a equal to b, b is greater than 0, so and of z is, and the last one lies on the negative direction of y-axis. Here you get a is equal to 0, x less than 0, so z is equal to minus 7 and is equal to 3 by 2. Let's discuss some of the examples for your polar form. Write the polar form for minus 1 plus 0 I. So a is minus 1, b is 0. We will put in your formula z is equal to 1. Argument for z is equal to pi, and then I write the polar form with 1 cos pi, because cos 180 the value is 1 and cos sine of 180 your value is 0. So you have to find such values of theta that both should match. Your theta should be same for both the functions. So let's say one more example, z is equal to minus 1 plus root 3l. So your a is minus 1, b is root 3. You will find your r, a square plus b square, that is 1 plus 3, that is equal to 2. Now here minus 1 comma root 3. Definitely it lies in which quadrant? Second quadrant. We discussed. And here you get cos theta is equal to a upon r, that is minus 1 upon 2. Right? After that, value of cos theta minus cos 60. Trigonometric functions, 180 minus 120, that is minus of minus cos 120. The answer theta is 120. Similarly, sin theta is equal to b upon r, that is root 3 upon 2. So sin 60 value is root 3 upon 2, which is nothing but sine of 180 minus 120. So you have to relate and get theta. So z is equal to r cos theta I sin theta. So 2 cos 120 plus I sin. You can redefine the function as 2 cos 2 pi by 3 plus I sin 2 pi by 3. Argand's diagram, certain examples. Let's say for z is equal to 1 plus 12. So this is z1, and z2 is set as 5 minus 7. And I have to plot the functions. You will get here somewhere. This is your 1 plus 2, your a is equal to 1, b is equal to 2. And 5 minus 7 will be in this quadrant. 5, and here somewhere 7, so this is your 5 minus 7. A is 5, b is minus 7, 5 minus 7. Just points are given. Let's say z1 is for 3 minus 5. Where will you plot? So you will plot here 1, 2, 3. Let's take certain functions. 2 is minus 5. Here you get your minus 3 comma 5, second quadrant, and 3 minus 5, 3 and minus 5. You will get in this quadrant somewhere here. 1, 2, 3, 4, 5, 6. I'm discussing for the square roots. For 8 minus 6, how will you proceed? Let the function be for a plus bi, where a and b both belongs to real numbers, squaring on both sides. What you get is 8 minus 6 at a plus bi the whole square. This is equal to a square plus 2abi plus b square I square. Minus 8 minus 6i is equal to a square minus b square. How you got this? I square is equal to minus 1 plus 2abi. So a square minus b square is equal to a real part together, imaginary part together. So minus 6i is equal to 2abi. What you get is a square minus b square is equal to minus 8. B is equal to minus 3 upon a. So b you got as minus 3 upon a. You will substitute in this equation which you got. So you get a square minus 9 upon a square is equal to minus 8. That is a raised to 4, 9 is equal to minus 8 square. Taking LCM, you get a raised to 4 plus 8a square minus 9 equal to 0. So a square plus 9, a square minus 9. These are your factors. So a square is equal to, let's say this is your 1 factors you are taking. So a square is equal to minus 9 and a square is equal to 1. Now as a belongs to real numbers, a square minus 9 is not possible, hence your answer has to be a square is equal to 1. So a is equal to plus or minus 1. Here you got your a. So if a is equal to 1, b is equal to minus 3 upon a, that is equal to minus 3 upon minus 3. A is minus 1. B is equal to minus 3 upon minus 1. the square root of following complex numbers. Example: 3 plus 2 root 10i. First step, your a and b both belongs to real numbers, which is in the form of a plus bi. First step, squaring on both the sides. So 3 plus 2 root 10i equal to a plus bi. So squaring on both the sides, your step will be 3 plus 2 root 10i equal to a square plus b square I square plus 2abi. Now I square is equal to minus 1. So 3 plus 2 root 10i equal to a square minus b square plus 2ab, equating real imaginary. A square minus b square is equal to 3, and next is 2ab is equal to 2 root 10. So, a square minus b square is equal to 3 here. B is equal to 2 root 10 upon 2a. So b is equal to root 10 upon a. Substituting in equation a square minus b square is equal to 3. Value of b, which is equal to root 10 upon a square minus root 10 upon a the whole square equal to 3. So a square minus 10 upon a square is equal to 3. LCM. So a raised to 4 minus 3a square minus 10 equal to 0. Taking factors, a square minus 5, a square plus 2 equal to 0. A square is equal to 5 or a square is equal to minus 2. But a belongs to real numbers and a square is not equal to minus 2. We would say a square is equal to 5. A is root 5, which can be either p plus or minus of root 5. When a is equal to root 5, b is equal to 10 upon root a, that is root 10 upon root 5, that is nothing but root 2. When a is minus root 5, b is equal to root 10, so b is minus root 2. 3 plus 2 root 10 is equal to plus or minus root 5 plus root 2i. Next,
Question on polar form. Question. One upon 1 plus I. Now first of all, we have to get it in the form of a plus bi. So rationalizing or multiplying, dividing with the conjugate of the denominator. So 1 upon 1 plus I into 1 minus I upon 1 minus I, that is equal to 1 minus I upon 1 square minus I square, that is equal to 1 minus I upon 1 minus minus 1, that is 1 minus, so half minus I upon 2. This is nothing in the form of a plus bi, so you get half plus 1 upon 2 minus I. So A is half and B is minus half. Taking R is equal to root of A square plus B square, that is equal to half the whole square minus half the whole square. 1 upon 4, 1 upon 4. You get 1 upon root 2. Now here it lies A comma B. Here A is positive, B is negative. It lies in the fourth quadrant. So cos theta is equal to A upon R and sin theta is equal to B upon R. Your values are half and minus half, which will lie in the fourth quadrant. We have the values. Cos theta is equal to half divided by 1 upon root 2, that is root 2 upon 2, 1 upon root 2. So cos theta is equal to cos of 45 degree, which is cos of 360 minus 315. So theta is equal to 315 degrees. Next, sin theta is equal to B upon R. Substituting the values, we get sin theta as minus 1 upon root 2. Now sin theta minus sin 45, which is nothing but minus sin of 360 minus theta, that is 315, and hence our sin theta, which is equal to sin 315, so theta is equal to 315 degrees. Next, we have to find certain values. Let's say Z1 is equal to 1 plus I, Z2 is equal to 2 minus 3I. We have to find Z1 plus Z2 with its modulus and individual Z1 and Z2 with its modulus, but we will add both of them. Now here modulus of Z is 1 minus I, modulus of Z2 is 2 plus 3I. You have to add both of them. You will get Z1 plus Z2, that is 1 minus I plus 2 plus 3I, 3 plus 2I. Z1 plus Z2 is equal to 1 plus I plus 2 minus 3I, 3 minus 2I, and the conjugate of Z1 plus Z2 modulus whole is 3 plus 2I. So this and this is same. Next, modulus of z1 minus modulus of z2 is equal to whole of z1 minus z2 modulus. So z1 minus z2 is equal to minus 1 minus 4i plus 4i. So the modulus will be z1 minus z2 is equal to 1 minus I, 2 minus 3i, that is minus 1 plus 4i. Your sign will change, so this both is same. Fundamentals theorem of algebra. X is equal to minus b plus or minus root of b square minus 4ac upon 2a. Here a, b, c all belongs to real numbers and a is not equal to 0. So the roots are in the form of ax square plus bx plus c. You will get the values. If b square minus 4ac is less than 0, then the roots are not real. Roots are not real. So let's take an example. 8x square plus 2x plus 1. You have to solve this quadratic equation. Given equation, your a is 8, b is 2, c is 1. b square minus 4ac is equal to 2 square minus 4 into 8 plus 1, that is 4 minus 32, that is equal to minus 8, which is less than 0. Then you can find the equation are not real in nature, I would say. So x is equal to minus b plus minus root of b square minus 4ac upon 2a. So minus 2 plus minus root of minus 28 upon 2a. So root of 2 plus minus 2 root 7i upon 8. Taking 2 common, you get 1 plus minus root 7i upon 8. So minus 1 plus root 7i upon 8 or minus 1 minus root 7i upon 8. One more question. A is equal to 2, B is equal to minus root 3, C is equal to 1. X is equal to minus b plus minus root of b square minus 4ac upon 2a if b square minus 4ac is less than 0. So let's substitute the values. This is given in the form of ax square plus bx plus c equal to 0. So a is 2, b is minus root 3 and c is 1. When you substitute the values, you get x is equal to, I would say b square minus 4ac is equal to minus root 3 the whole square minus 4 into 2 plus 1. 3 minus 8. So minus 5 is less than 0. X is equal to minus of minus root 3 plus or minus root of minus 5 upon 2 into 2. That is 3 root 3 plus or minus root 5 I, because this minus 5 can be split as minus 5 into minus 1 equal to 4. 2 2s are 4. Root 3 upon 4 plus root 5 I add. These are the two values. Solve the quadratic equation. X square plus 3ix plus 10 equals. Next, b square minus 4ac is equal to, your a is 1, b is 3i, c is 10. Substituting the values, 3i the whole square minus 4 into 1, that is minus 9 minus 40, that is minus 49, which is less than 0 because I square is equal to minus 1 here. Now as these are less than 0, x is equal to minus b plus minus root of b square minus 4ac upon 2a minus 3i plus minus root of minus 49 upon 2 into 1. So minus 3i plus minus root of minus 49 upon 2. So x is equal to minus 3i plus 7i plus minus 7i upon 2. If it's plus or either it is minus, so minus 3i minus 7i upon 2, 4i upon 2 minus 10i upon 2 is equal to 2i, x is equal to 5i. If x square minus 2 plus 1 ix minus 1 minus 7i is equal to 0. Here a is 1, b is minus 2 plus I, c is 1 minus 7i. So b square minus 4ac is equal to minus square minus 4 into 1 into minus 1 minus 7i. So 4 plus 4i plus I square plus 4 minus 28i, that is 7 minus 24i. These are the roots. So roots are given as x is equal to minus b plus or minus b square minus 4ac upon 2a. So 2 plus I plus or minus 7 minus 24 root I upon 2. 7 minus 24i is equal to a plus b. Taking squares, you get 7 minus 24i is equal to a square plus I square b square plus 2abi. So 7 minus 24i is equal to a square minus b square plus 2abi. A square minus b square is equal to 7. 2abi is equal to minus 24i. Real, imaginary. A square minus 12 upon a square is equal to 7. So a square minus 144 upon a square is equal to 7. Taking LCM, a raised to 4 minus 144 is equal to 7a square. A raised to 4 minus 7a square minus 144 equal to 0. Square minus 16 square plus 9 equal to 0. So a square is equal to 16, a square is equal to minus 9. A square has to be equal to 16. A is either plus or minus 4. When a is positive 4, b is equal to minus 12 upon 4, that is minus 3. And when so our roots are 7 minus 24i is equal to plus or minus 4 minus 3i. X is equal to 2 plus I plus minus 4 minus 3i upon 2. So 2 plus I plus 4 minus 3i upon 2, or 2 plus I minus 4 minus 3i. Okay. So x is equal to 3 minus I, or x is equal to minus 1 plus 2i. One more question. Let's say x square minus 5 minus ix plus 18 plus I equal to 0. A is 1, B is minus 5 minus I, C is 18 plus I. So B square minus 4AC is equal to minus 5 minus I square minus 4 into 1 into 18 plus I, 25 minus 10I minus 1 minus 72 minus 4I. So minus 48 minus 49. Given equation, x is equal to minus b plus or minus root of b square minus 4ac upon 2a. You get minus 5 minus I plus or minus 48 minus 14 upon 2 into 1. So 5 minus I plus minus 14 upon 2. Let root of minus 48 minus 49 be equal to a plus bi. Squaring on both sides. Minus 48 minus 49 is equal to a square minus b square plus 2abi. Equating real and imaginary. A square minus b square is equal to minus 48. B is equal to minus 7 upon 8. So a square minus 7 upon 8 square is equal to minus 48. Square minus 49 upon a square is equal to minus 48. 8 raised to 4 minus 49 minus 48 square. So 8 raised to 4 minus when comes here becomes plus, minus 49 equals 0. Factors: a square plus 49, a square minus 1 equal to 0. So a square is not equal to minus 49 and a square will be equal to 1 because it cannot be negative. A has to belong real numbers. So a is either plus or minus 1. If a is plus 1, b is minus 7 upon 1, that is minus 7. And if a is 1, minus 1. Minus 48 minus 49 is equal to plus or minus 1 minus 7. X is equal to 5 minus I plus or minus. X is 3 minus 4i or x is 2 plus 3i. Now coming to new concept of cube root of unity. Here we will say x cube is equal to 1, x cube minus 1 is equal to 0. So x minus 1, x square plus x plus 1, these are the factors. So I will say x is 1 or minus 1 plus or minus root of b square minus 4ac, b square minus 4 into a into c upon 2a, 2 into 1. So other side x is equal to minus 1 plus root 1 minus 4 upon 2. So x is minus 1 upon 2 or plus or minus 3 upon 2. Or x is 1. So cube root of unity, where x is 1, minus 1 upon 2 plus or minus root 3 I upon 2. So factors will be same as we did for x. Now since this is not equal to, let's say, 1, we have to take this factor, unity plus 1 equal to 0. But we have said this is equal to 1, then we get the values are found. So all for unity. Now if I say I have to find the value of unity 80, that is 1 raised to 6 is small. Let's say minus 30. But minus 10, that is 1, because the path is an even number. 1 more. Minus 35, that is 1 raised to minus 35, that is minus 1. Find value of the sign is the complex cube root of unity. We know that cube will be equal to 1. So let's say I have to find the values for these two. LCM. But this is also equal to, so my answer is one more example. We will take one of them common from each. Now this whole thing is equal to 0. How did you come to know it is equal to 0? Because this is equal to 1 and 1 plus this is equal to 0. And this terms you will get the answer. Example. This is minus cube, that is minus 1. Okay, here we end the synopsis. Here we discussed at the very first start of the chapter, we discussed the conjugates. After conjugates, we discussed the amplitude, modulus. We divided the equation in the form of a plus bi. Next we continued with the value of I, where we solved certain examples for it. We found the value for an equation where we use synthetic division. For finding the value of, we found the square roots of equation. Later on we continue with the polar form. We define the values for sine and cos. Then we discuss Argand's diagram. Proofs. And then cube root of unity, quadratic equation.